welcome everyone. I can see we have 137 participants. That's a well-attended meeting, so I think we're going to have a great meeting. So to start things off, I'd like to hand things over to John, and who will give a welcome.
Well, thank you, Dave, and good morning, everyone. Good afternoon, good evening, wherever you may be. Welcome to our first Ivan Zoom meeting for 2022, as Dave just mentioned. I think I see we just blipped up to 142 people, and yeah, very good attendance today. We certainly appreciate everyone joining in. And as far as Ivan for 2022, got a lot of good stuff going on, and we'll get into that in just a few minutes. Today's meeting, of course, is on the topic of Benchtop NMR, something that I think this is the first time we've covered that topic in our meetings, and certainly a number of manufacturers in the Benchtop NMR field. In fact, today we've got Sean Krakiewski, CEO of Nanalysis, with us in the audience, along with Bruce Licks from Nanalysis. Very anxious to get down to business in just a few minutes on today's topic. MR Resources, of course, is very happy to be sponsoring the Ivan meetings. We're in our altogether, I think, 5 or 6 years at it now, and a couple of years worth of Zoom meetings. I think this is number 26 or 7. Certainly been going on for quite some time, and we're very happy that I think we're maybe doing a pretty good service for the NMR community. As I mentioned, MR Resources are very happy to sponsor the meeting, all of the meetings. Company's been around for 35 years now, a very good line of reconditioned NMR spectrometers, along with services, quench recoveries, relocations, and the like. Our sister company, Q1 Instruments, a little bit newer to the industry, but very, very good and very capable line of brand new NMR systems from 400 to 600 megahertz. I believe Don Bouchard of Q1 is in the audience with us. Don, would you give a few words on Q1, please?
Q1 is dedicated to developing NMR hardware and software to make routine NMR more accessible. Our products include complete systems at 400 megahertz with Oxford technology magnets manufactured by Q1, complete systems up to 600 megahertz using refurbished magnets from MR Resources for a price that will surprise you. Console upgrades up to 600 megahertz, which include the economy upgrade, which utilizes the existing probe and shims at an aggressive price, and a full upgrade, which adds broadband STM probes and sample changer for a completely automated system. And we also offer our Smart Tune and Match probes for Brooker and Varian systems for improved performance, throughput, and reliability. 3 new installations of the Q1 systems at 3 locations in North America include a 400 megahertz instrument with the Quantum 1 console at a company specializing in silicon compounds located in Toronto, Canada, a 400 megahertz Quantum 1 Plus system at a manufacturer of dyes for a global eyewear company, and a complete conversion of a 300 megahertz spectrometer for a manufacturer of adhesives and resins with excellent performance owing to the enhanced 23-channel shims for the SpectraSpin magnet. Want to know more about our probes, consoles, and complete systems? Contact us for information at q1instruments.com. We'll be happy to arrange a remote demonstration. Thank you.
Thank you, Don. Very good, very capable lineup of NMR spectrometers, and certainly bringing a bit more competition, much needed competition, I might add, to the industry. Krish, over to you for a moment or two, if you would. Could you let us know about upcoming Ivan Zoom meetings, please?
Thank you, John. Welcome, everyone. Happy New Year. Hopefully 2022 would be better than 20 and 21. I just want to talk about what is coming down the pike. Next month, February 24th, we have a panel discussion on advanced NMR analysis methods for challenging spectral data sets. This will be led by Dr. Michael Bernstein of Ambien Analytical. Mike will be joined by Professor Daniel Holland, University of Canterbury in New Zealand, and Professor Eric von Harbau at Technical University of Kaiserslautern in Germany. It's on February 24th. Watch for invitations for that, registration for that. In March, we have Professor Patrick Guerrero from Nantes giving round 2 on QNMR beyond 1D proton spectra. And we have May and June are almost finalized. I will announce that soon. And we certainly are excited to work in April along with ENC. I will let John talk about at this point if he needs to. So with that, I welcome all of you and thank you, John. Back to you.
Thank you, Krish, and very good lineup of meetings out for the next several months. And well, of course, the big news, as you mentioned, that hopefully everything is going to be live at ENC end of April at the Cypress Grand Hyatt in Orlando, Florida. At least as of today, things are still up and running, and let's keep our fingers crossed, hope for the best. Ivan is going to have a suite all week at ENC in conjunction with MR Resources and Q1. But of course, the big day, Saturday, day before ENC, we'll have our traditional day-long Ivan meeting, both going to be in person and virtual as well. We're referring to it as a sort of a hybrid meeting, if you will, a live audience, live speakers, and online audience and online speakers. And we're hoping for, well, we're hoping to be able to do the live component. And again, we're keeping our fingers crossed on it. Nightly at ENC in the Ivan suite. Can't fill you in too much right now, but we've got some great and really worthwhile surprises coming up every evening. Incidentally, for the Saturday meeting, we're putting a call out for any speaker or speakers that would like to present on the topic of NMR spectroscopy relative to COVID-19 vaccine development. And anyone in the audience or any of your colleagues or associates that you'd like to point in our direction, please do. All that said, without further ado, Dave, will pass to you. If you could give a couple of words maybe on the second Ivan Founders Award, very important component of the Ivan day before ENC meeting. And after that, Dave will open the meeting. Dave, over to you, please.
Okay, great. Thanks, John. So what John mentioned is that at this year's Saturday meeting, we will be giving out the second annual Ivan Founders Award. And right now we are soliciting nominations for that award. And I just wanted to give we're hoping to get nominations from all of you. And we have a committee in place that will decide on the lucky winner of the award. As with last year, there is a cash award associated with the Ivan Founders Award, and one will also receive a trophy, which I presume again will be one of these nifty MOVA globes that resemble our logo. I ask everyone to submit nominations. First of all, the committee will be for deciding on the winner. Right now will consist of John and the original board, Krish, Dan, and I, and Ken Knott, who received the award last year. In the future, the board will generally bow out and until the nominating committee is made up entirely of John and award recipients. We ask you to submit nominations, and with a deadline of about April 1st, so we can have time to decide before the 23rd. And all we're asking is basically a one-page document by email and to ivanInfo@ivanNMR.com. And on that one-page award, you just need to name the one or more nominees with all their information, and of course, give the information about you as the nominator. The page should include a short paragraph explaining why this person is being nominated. Doesn't have to be lengthy. Probably we all know who the nominee is anyway, and a few references to exactly why they're being nominated. For example, was it a conference they held or a training course that they gave? And this document will go out and with some advice for making the nomination, but basically the winner of the Ivan Award should be an individual who has done service to the NMR community within the scope of Ivan, which is to enhance communication and education of all of us in the NMR community. So I look forward to your nominations. Feel free to contact any of us on the board as well. We're happy to discuss your nomination with you. So without further ado then, let me hand things over to Paul Bowyer, who will introduce our panelists today, and let's get started.
Thanks everybody for joining us today for this Ivan meeting. It's good to see so many people here, and actually good to see so many familiar names, and we look forward to catching up with a lot of you at some point in the near future. I'd just like to thank the Ivan committee for inviting me to chair today's meeting. I'm very happy to do that. The title of today's session is Benchtop NMR Opportunities and Challenges. Now, we've got quite a packed program today. First up, we've got Professor Kate Kemsley, from the head of core science resources at the Quadram Institute Bioscience at Norwich here in the UK. Then we've got Dr. Maria Silva Elipe, who is a senior principal scientist at Amgen. Then we have Dr. Travis Gregar, who is a senior specialist at 3M in Minnesota. And finally, we've got Dr. David Foley, who is a principal scientist at Merck in New Jersey. Now, our panelists are going to give talks. We're not going to have much time to do Q&A between the talks, but I strongly encourage you to actively participate, ask questions via the chat window. I will be looking at the chat window and fielding questions to the panelists after each of them is, well, after everybody has given their talk. So, and we'll also open up the mics and try and encourage some lively discussion around the whole topic of Benchtop NMR. Now, before I hand over to the panelists, I thought I'd just set the scene for today's meeting by just giving a very brief overview of Benchtop NMR. With a very short bit of history and just some of the developments that have taken place in the last decade or so. So if we wind back, say, to the early days of NMR spectrometers, those spectrometers were based around permanent or electromagnets, and they were relatively large, and they were CW, they were continuous waves. So we've got a couple of kind of examples from the early days of NMR here. We've got a JEOL JNM1 with a proton frequency of 32 megahertz, and we've got a Varian A60 with a proton frequency of 60 megahertz. So these are fairly hefty beasts. You wouldn't put one of these on a benchtop, it's fair to say. Now we all know what happened next when it comes to the development of NMR spectrometers. Superconducting magnets arrived on the scene, and they were facilitated a significant increase in B0 field strengths. And as a result, permanent magnet-based designs and electromagnet-based designs for NMR kind of fell by the wayside or sidelined, certainly for high resolution NMR anyway. That is until kind of like the mid-noughties, when there was renewed interest in developing permanent magnet-based NMR spectrometers that utilize newer designs, newer materials, newer manufacturing methods to be able to make truly benchtop size NMR spectrometers. But those spectrometers also take advantage of the kind of developments that happened in the preceding sort of half century or so, such as improved electronics, improved computing power, vastly improved computing power, and other developments, Fourier transform, for example. And so there's been a lot of development since the mid-noughties in terms of developing true benchtop high resolution spectrometers. And if we sort of fast forward to today, as John mentioned, there are actually quite a number of benchtop vendors developing and selling benchtop systems. So it's quite a competitive environment now, but it's quite an exciting sort of environment as well. And I think the competition between the different players in the benchtop space is really helping to drive benchtop technology forward. Now, if we think about benchtop NMR systems, it's quite easy to see why a benchtop system might be quite an attractive proposition. You know, high field, if we compare to high field, we can see some advantages of benchtop. I mean, high field instruments are obviously very powerful instruments, and we all love high field NMR, but that power comes at an expense. And certainly some of that expense is a financial expense. So for some people, high field NMR, or some institutions or some companies, high field NMR simply just isn't an affordable option for them. Not just because of the initial financial outlay, but also the upkeep and the maintenance and the supply of cryogens, for example. And also the housing of a high field instrument. Typically, you need to put it in a dedicated room and have a specialist to kind of look after the instrument. Now, if you think about benchtop instruments by comparison, they are without exception much more affordable. They require very little maintenance indeed. And of course, being permanent magnet based, they're cryogen free. And the other really important advantage for benchtop in some environments and some applications is that you can site the instrument next to where you're doing your research or doing your chemistry. Now, of course, it's not all, you know, the benchtop is better than the high field. There are some trade-offs, and we all know here what those trade-offs actually are. So, and it comes down to performance. So a typical, and this is kind of illustrated, certainly one aspect is illustrated by this spectrum here as steroid. So the bottom spectrum is the proton spectrum of the steroid collected at 500 megahertz, and the top one is collected at 60 megahertz. And in going to a lower field, you have lower dispersion, which means you're going to have more signal overlap, which is, for some applications, is going to be a problem, of course. The other hit that you pay by going to lower field is sensitivity. So the sensitivity of a benchtop instrument is, as with dispersion, is typically of the order of magnitude lower than a high field instrument, depending on which benchtop you're comparing with which high field instrument. So, you know, those are the trade-offs here, and they can be problems. So naturally, obviously, there's been a push to try and drive B0 field strengths for benchtop systems higher and higher. If we go back to, say, 2010, which is when I think the first commercially available benchtop systems came out, and by that I'm talking about sort of FT systems, not time domain systems, commercially available instruments came out. They had, I think the first one was a picospin 45, and that had a proton frequency of 45 megahertz. But in the ensuing decade, field strengths increased, and we're now at a point sort of here in sort of 2021, 2022, where we have systems that have a proton frequency of as high as 125 megahertz. So obviously going to higher field is going to help with dispersion and can, depending on the instrument design, obviously help with sensitivity as well. Now, as well as improvements in magnet and going to higher field strength, there have been other recent developments in benchtop hardware that have kind of features that we take for granted these days on high field systems, but they've migrated onto benchtop systems, such as pulse field gradient capabilities, which allows you to do things like diffusion measurements, of course, and also can be useful for more advanced experiments, multi-pulse experiments or 2D or experiments where you can use those gradients for coherent selection. The other feature that has been recently introduced as an option on a number of benchtop systems is auto samplers. And also another sort of relatively recent feature is the availability of systems that have true kind of multi-nuclear capabilities, where you can actually tune to a wide range of nuclides and all within a single instrument. So these are all really nice, welcome developments that really enhance the performance and usability of benchtop systems. Now, in tandem with sort of hardware developments, there's been a push to basically implement more advanced pulse sequences and experiments and methodologies on benchtop systems. So
I'll carry on. Hopefully I can pick up a little bit where Paul was going to go with showing some instruments. In fact, I've got one on my title screen there. That's our Oxford Instruments Pulsar Benchtop NMR Spectrometer, which is the machine that I've used throughout the work that I'm going to present today. So hello everybody, I'm Kate Kemsley. I head up the Core Science Resources team at the Quadram Institute Bioscience in the UK. And today I'll talk you through some of our recent work using that instrument for authenticating the species of ground roast coffee. And we've taken that work all the way through from initial studies, probably about 4 or 5 years ago, to a fully working commercial application. So I've got one slide of background on the issue. So here's my one slide of background on the issue of coffee authenticity. So as you're, I'm sure, aware, coffee is a huge trading commodity. It's grown in numerous developing countries across the tropics, but it's consumed all over the world. And what you may not know is that just 2 species of coffee make up nearly all commercially cultivated beans. So these are Arabica and Robusta. Arabica is harder to grow, but it's much more in demand because it tastes much better than Robusta, which is really quite an acquired taste. And in practice, it only gets used in lower grade coffee products and blends. And that's reflected in the trading price difference, so that Arabica beans often trade at twice the price of Robusta. And that, along with the long worldwide supply chain, means that Arabica coffee is really quite vulnerable to fraud, because as you see from that picture there, once beans have been roasted and then ground, you'd have no chance of being able to tell that there are actually 2 species present in that little figure. So some sort of analytical test is needed at points in the supply chain, and we wanted to find out if Benchtop NMR could tackle this problem. Now, why did we think that it might? Well, our starting point was existing knowledge of coffee metabolomics from work on high field, high resolution NMR spectroscopy, which started a few years ago, not just by us, but other groups around the world, on extracts from coffee beans, where we were looking for compounds that could differentiate between the various species. So what I've got here is a proton NMR spectrum taken at 600 megahertz of the lipophilic phase. So this is ground roast coffee extracted using chloroform. And as you can see, it contains a large number of peaks, and they range in size. Some are off the scale, so I can show you the lower end of the scale. And these are from primary metabolites, so things like triglycerides, all the way down to minor compounds and breakdown products, which can vary a lot, which come from the roasting process. Now, on the next slide, I've added the equivalent 60 megahertz benchtop spectrum from the same extract. And you can see, obviously, it looks quite different. We've got, much more overlap peaks. And because of that lack of sensitivity, only the more major compounds can be picked out. So what have we got in terms of major compounds? Well, we've got the triglyceride resonances, and actually coffee beans are quite oily. So the seed kernels contain typically about 15% by weight of fats. So in the lipophilic phase, they're the dominant features in the spectrum. Of course, it wouldn't be coffee without caffeine. And these have also got clear, easy to recognize signals at both field strengths. There are various other things in there which you can't see at 60 megahertz, but this little peak here is a really important one. It's isolated, which is nice for us, and it's from a compound called 16-O-methyl-caphestol, or 16-OMC. And this is a diterpene, and that's a class of secondary metabolites found in coffees. And this is a really very interesting peak for us because it seems to be absent in the extract from Arabicas. So the bottom of those two spectra is the Arabica spectrum, and you can see that it's more or less absent in that region completely. It was identified as a marker compound for Robusta in chromatography studies sort of 20 years ago. And the thinking then was that if you found 16-OMC in a coffee sample, then it couldn't be a pure Arabica. So at this point, when we found this in our comparative spectra there, we felt lucky because that peak is pretty much isolated on an empty-ish region. It's not overlapped by the triglyceride signals nearby or the caffeine, and that's really just luck. We happen to get lucky at 60 megahertz. Actually, at 40 megahertz, it is overlapped a bit more by the bisallylic peaks in the triglycerides. But that suggested to us that we had a route to a simple, low-cost coffee species authenticity test. So our next step, thinking about the sensitivity issue, was to establish whether or not we could see that same peak, not just in a pure Robusta coffee, but in a mixture with Arabica, and at fairly low concentrations, so below about 15% by weight. That's the type of fraud that's most likely to happen. When you get to sort of 30–40% Robusta, which also a fraudster might want to do, actually you can taste it. Robusta is so distinct from Arabica that you wouldn't be able to pass off that coffee very well as an Arabica. But down at 8%, like I've shown in this close-up here, we still get quite a visible signal. You can see that just by eye, that there's a clear little blip there. And actually on the right-hand panel, I've got even more of a close-up on that 3.16 region. And you can see even at 4%, 2%, there's a blip. I mean, they're not brilliant spectra, they're noisy. We can clean things up a bit, which is what I've done here. So a good technique to use is matched filtering when you're looking for a single signal against a background of white noise, and we get much clearer, cleaner peaks then. So at this point, we're all feeling quite optimistic, but for completeness, we analysed the pure Arabica coffee that was used in making these blends. And these are going to be the black traces in my next figure. So you'll see that both in the unprocessed and the processed spectrum, there's still clearly something there. There's still a peak. So yeah, we found Arabica coffee, there's something there. What's going on? Shouldn't be any 16-OMC peak, or so we thought. But we repeated this experiment over and over with different coffees and different Arabicas, and the results really did stand that there is a small amount of 16-OMC there. So our benchtop work was the first to find this. This was a new and really quite controversial finding in the coffee sector. The consensus had been for years that this compound should not be there in Arabicas. But the reason really was that our protocol, or our preparation protocol, I should say, was more sensitive than the historical work. And that was to do with the fact that we started with a larger amount of coffee and concentrated it up. And that's a very different sample prep to the reported chromatography methods, where they'll use typically much, much weaker samples. Nevertheless, because we were looking to overturn 20 years of literature, we had to really verify this finding quite exhaustively. So we obtained a collection of completely authentic Arabica beans. These were so authentic they'd actually been collected by the researchers at the Royal Botanical Gardens in Kew Gardens in London. from the plantations around the world themselves, and they'd had genomic studies done on them, and they knew the provenance of them all down to the individual bush, I think, in some plantations. And we found low levels of 16-OMC using our benchtop method in all of them. We had to verify these findings by the techniques, and that included high field NMR and also LCMS and some other methods. I won't go into those ones here, but I will show you the high field data because this is quite interesting. So this is a series of blends made up between 0 and 15% weight for weight Robusta in Arabica. The bottom three are 100% authentic Arabicas, and I've highlighted with the red circle that marker peak there at 3.16 ppm, and clearly there's something there. So we do see that by 600 megahertz. So we integrated the area of those peaks in the normal way, and we run the same samples through our 60 megahertz machine. And in this next slide, I've got the results for that peak integral from 60 versus the 600. And we were really pleased with this result because it means that for this application, you don't get any significant gain from using high field NMR spectroscopy. And that was really good news for us and for our benchtop instrument, because it meant that going forward with developing this as a commercial method, we could use our benchtop NMR. And that's obviously much, much cheaper in terms of usage of floor space, of consumables, and our kind of full economic costing of hourly usage. So having established that pure Arabicas do contain small amounts of that 16-OMC, we couldn't any longer use this as a simple presence-absence marker. So instead what we need at this stage is a threshold of some kind to decide whether any amount of 16-OMC found is consistent with pure Arabicas or not. So we obtained the peak integrals from our complete collection of assured provenance samples and constructed a probability density function to describe the distribution of those measured peak areas. And that collection included both commercial cultivars, which was the most important series to us, but also some wild types from Ethiopia, which is where all coffee comes from originally. They're the few outliers on that plot. They tend to be a bit more variable than cultivars. And then we set a threshold at our required accept-reject ratio, so whatever probability we want to work at, and that's the kind of balance between false positives and false negatives. And then once we've done that, we can accept or reject incoming samples where we don't know anything about them as either Arabica or not. Then finally, we integrated all of this into a simple app so that our technician could carry out this method in a straightforward way, collect the spectrum and then analyze it with a single click. And this is what the interface looks like. So here I've got it analyzing a pure Arabica. This is what we see. We get on the large upper panel, we get the raw 16-OMC region. And in that sample, there's just that hint of a peak there. The lower panel represents our PDF. And on that density function, we put a black marker to show whereabouts the present sample is located with respect to that distribution. And this one's bang in the middle, meaning that we're going to accept it as consistent with Arabica. Here's another test sample being analysed. So this one was prepared using just 3 Robusta beans per 100. So that's 3% roughly weight for weight Robusta in Arabica. And now you can see you're in the situation again where by eye we can even see that there's a peak there in that large upper panel, and below you can see that's falling well outside the normal range for Arabicas. So we reckon our detection limit by this is around about 1.5% weight for weight Robusta in Arabica, and below that you couldn't really say whether you were dealing with an unusually high containing pure Arabica or whether you were dealing with an adulterated sample. And then my last sample that I'm going to look at here, this is a retail purchase coffee that was labelled 100% Arabica, and it clearly isn't. The 16-OMC peak there is huge. It's almost off the scale. And our best guess is that this coffee contained actually about 20% Robusta by weight. So that retail sample was part of a wider survey of coffees that we carried out, and they were obtained from around the world, and we did find significant fraud in the sector. We wrote that up in the more recent of these two papers. They're both in the academic literature, but they are open access, so you can click on those ones and get the full story. That takes us back to our original work all the way through to the complete screening protocol. And we now offer that service through our commercial subsidiary to the coffee industry. And that's a thriving service, actually. We do dozens of samples a month for various clients around the world. And actually, you can see the inside of our lovely new laboratory building on a video, which is on the commercial subsidiary site there at qibextra.co.uk. And my final slide I'd like to leave you with is an acknowledgement of our many funders and collaborators on this work. A special shout out to Oxford Instruments, who we've worked with since about 2013, funded by the Technology Strategy Board, or the UK's Innovate UK grant funding body, and the sponsors of the Quadram Institute, which is the BBSRC, the Biotechnology and Biological Sciences Research Council, and our various other collaborators at various times. And with that, I'll say thank you for your attention, and I hope you've been able to hear me throughout.
Thanks very much, Kate, for that. I think I'm back. I hope I stay back. Fantastic. Okay, brilliant stuff. Yeah, that was a great talk, Kate. I think it was a really excellent example of a really brilliant application of a benchtop system. So just coming back to when I was talking, I don't know when you lost me. All I know was that somebody sent a message saying my audio is unstable, and before I knew it, I was completely kicked off my internet. But I think, rather in the interest of time, I think we should move on actually to the next speaker, which is Maria. So Maria, if you could take it away, that would be great.
I am Maria, working for Amgen, and one of the NMR people enjoying with all these fun machines. So what I'm trying to bring here to the audience is our path from the 45 megahertz benchtop NMR to the 400 cryogen-free NMR. So I just want to show you the Ambien Path we went through, focus on reaction monitoring, examples. I'll try to minimize explaining the examples and our lessons learned. So this is our path. So we started, and I think I'm going to try to put the pointer so I can point out things. We started with what we call it the shoebox. The picker spin is as big as a shoebox. So very simple system to do, and I'll show you an example in the next slide, reaction monitoring, and then we jump into a different beast. It's a 400 cryogen-free NMR. We call it cryo-free NMR. I don't like to be on pictures, but I am a short person, and the magnet is short like me, and we installed it in the chemistry lab. We wanted to be integrated with all the chemistry people and instruments. And we tested in a simple manner with a simple reactor, the online protonated solvents reaction. And then we have right now, we evolved to our kinetic platform. We also do some reactions on the tube, especially like a photochemistry, following Janine's papers with all the things. I'll show you a little bit some examples. And I want to really talk about the people on the right here, on the bottom right. I'm very grateful to work with James. James Murray has bring to Amgen an incredible expertise on kinetics and really improving our processes tremendously. So I'm just joining this group with the NMR. And then we also have other great engineers. So Andrew and Derek, they bring other techniques like a calorimeter and many other things. So the first example I'm showing you here is with the picker spin, 45 megahertz. We were looking into an example that would be difficult for other techniques. So the reaction we were looking into, one of our projects, didn't have basically chromophores to follow by HPLC. So that was an advantage for NMR because it doesn't care about those things. Also, we were having a proton that we follow the reaction in the product that is type of aldehyde type, a vinyl proton, far from the solvents. But this reaction was having another problem. It was a biphasic. So the chemist working with me, he was running a big reactor. He took aliquots from the reaction. He quenched the reaction and he centrifuged to give me the organic layer. And then I injected in the picker spin and I just plotted it at the different times. We knew with QNMR at the end of the reaction how much product was formed, so I was able to calculate back the concentrations. Obviously, this is very simple, but we got an important point. The reaction happens in 2 hours, while the chemist was waiting for 6 hours because didn't have a real tool to look into how long it takes the reaction. So that was an important information. So then we jump into this project of this, we call it TrioFree NMR. So this is an HTS magnet that is a high temperature superconducting magnet, so that doesn't require any liquid cryogens. So that was a project sponsored by Amgen to build the first 400 cryogen-free NMR by HTS 110 in New Zealand. And Bruker committed to us with integrating a standard console and a standard probe and tested the magnet. I have to be very grateful to Dave Foley and his team when he was at Pfizer, because they were the first ones having the 200, and I visited them and I learned so much from them that thanks to them, we are successful today. So really, thank you, David. So, so this magnet, just show you very briefly, this system has this little magnet, short like me, is in the hood in the chemistry lab, and it has connected to a big tower here, which is in the corner in the lab. It has a helium compressor and a power supply because it's cooled by helium gas. And then on the back, we have an air chiller. We didn't have options to do the water chiller. And it's, I don't know if you see here on the back of the picture. Then we have an nanobay console, which is very small. It's actually hidden in a space in between the two hoods in the lab. You cannot see it, and the computer. In these papers, we proved that the data coming from this system is comparable with any 400 cryogen NMR. I'm not going to discuss that because my focus here is reaction monitoring. Now, we wanted to make it more difficult. So let's do online protonated reaction. See if these magnets can handle it. So anyway, so we looked at that simple model, but practical. So we did these RCN reactions with the ruthenium catalysts. So because we use this type of reactions to do this cyclization, and we did protonated solvents. We follow the paper that published this information, this reaction. They were testing different catalysts. We choose one of them. But they test the reaction in the NMR tube. So we basically increased the scale 30 times because we use this small round bottom flask and more volume. And then we just simply look into following, concentrations versus times of the methylene protons of the starting material and the product, and get the rate constant. The point here was not really the rate constants, is to test the system if we can do this type of work with this magnet. Let me show you something interesting. You can see here. So I did 1D proton and 1D wet. You can see that normally reactions, there are changes going on, whether it's obviously changes of concentrations. Sometimes, depending on the condition of the reactions, could be changes of pH. Those affects the chemical shifts. So you can see at the beginning of the reaction, there's a lot of shifting of the chemical shift. There is a difference between the 1D proton and the wet, because the wet is suppressing the solvent, and the system look at the tallest peak, and the sign, this is the solvent signal at a certain ppm. So it cannot control a little bit more because of that routine, the movement of the signals. At the end of the reaction, when there is really nothing happened, everything is done, you see still some shift of the signal, and this is more reflecting, in this case, the drift of the magnet. This magnet drifts on more than the standard cryogen magnet. But with software, where I use NOVA, you can align the signals and get your concentrations versus time. So now, I'm going to show you examples that show real life. So once we proved the concept, we went to examples, some of them done in NMR tube because corrosiveness and exothermics and gases producing. So, but we solved important problems that were critical in the manufacturing part. So here is one of them. And this is when I met James and worked with him, and we actually very, very successful working with James. So in this bromination reaction, we follow the reaction by NMR using fluorine for the fluorinated species and proton for the MBS, which is the substrate, the important reagent, not the substrate, the reagent, and the succinimide. So there is potential ideas that MBS or molecular bromine could be the brominated agent. So the problem was we were using portion-wise adding MBS, but when we scale up the reaction didn't go so well. So that's why we came to look into the NMR to see if we could propose some information and understand what is happening. And we were able, using these techniques here, reaction progress kinetic analysis and variable time normalization analysis, which is at least a couple of papers here listed if you're interested. We were able to calculate the order of the species by simply plotting, instead of concentrations versus time, plotting concentrations. We ran 2 reactions, changing only the concentration of one species, and then we plot concentrations versus the time integral of the concentration of the species. We are changing concentrations, that is with the exponent of the order of the reaction of the species that we can calculate it when they overlap because they don't depend on concentration. We were able to calculate all the orders and understand better what was happening on the reaction and understand that the bromine, molecular bromine, was actually the brominated species needed to be in the solution all the time to have the reaction going. So we changed the process in the manufacturing plant. Instead of portion-wise, added continuously, and we got all these benefits. It decreased the reaction time, decreased the amount of MBS needed, reduced the number of impurities, less polymerization, and increasing yield. Very successful. Second example is a typical nitration reaction. So we modify based on OLAB conditions to get a good yield, but we were having a surprise when we add water. The reaction was going even faster. This reaction was done with TMS chloride, which is very expensive, and ammonium nitrate, which is explosive. So we have to be careful when you scale up, right? But the fact that we add water, which was not, it really makes the reaction go better. We wanted to understand what is the role. So another work that I participated and worked with James, I'm very successful. So we look into the difference between adding water and not adding water. This is NMR data, concentrations versus time. When we add water, when we don't add water on the left, we have a 5 hours of induction period until we can see product formed. When we add water, the induction period is very short, less than an hour or so, and we see product forming. We see right away fast the conversion of TMS chloride to hydrolysis to the OH, and we don't see much really forming any impurities or things like that. So really that was an indication that TMS nitrate should not be the nitrated agent that it was expected to be. So we think that with water, the hydrolysis of the TMS chloride goes faster, facilitates the dissociation of the ammonium nitrate, basically forming nitric acid that we think is the real nitrated agent and forming the nitration. When we don't have water, we have an equilibrium between the boronic acid and the boroxine trimer, which slows down the whole process and it creates problems. So that was important because we basically changed the reaction. We don't have to use TMS chloride, very expensive. We don't have to use ammonium nitrate, explosive. So we can use a straightforward fuming nitric acid that we propose that it forms and this NO2 radical that is that has the role of nitrate, and we really were very successful. But there is a caveat. This reaction is very exothermic. And NMR participated on the study for the safety, which is good. We compare, I'm just gonna explain a little bit this graph on the right. We compared the data from calorimeter and NMR, and they all gave the same information. So I was really very happy. So the data from NMR is coming from the dots, and the calorimeter is the straight line. So this is a comparison of 2 reactions with different dilution of fuming nitric acid to understand the amount of heat release. And so we understand that you have to control the dilution of the nitric acid to be on the same side. And the last one is coming back to this bromination reaction. We wanted to be more efficient in our process. Instead of having different steps on the reaction, the bromination and others to form our intermediate, what we wanted to do is one-pot reactions where we do different things and we get the the product we want at the end. Try to avoid workups, minimize chemical waste. So we wanted to replace the radical bromination by a photobromination. So our chemists did a lot of work finding out the best conditions for reducing the reaction from 6 hours to 15 minutes by changing solvents, temperatures, but they did it in a very laborious way. So they have an LED lamp, they have NMR tubes around. When there is no light, not LED lights, there is no reaction. So they took each NMR tube at different times, go downstairs to the basement, go to the open access, put it on the rack and request an inspection. That is a very lengthy process. So we use Janine's approach in her paper using Janine's from Merck, using the NMR tube from New Era, the photo NMR, and using the light source for us with the appropriate wavelength. And we basically replicate, and put it on the magnet, we basically replicate the profile that our chemists got with few NMR tubes. But we, with having the NMR tube inside the magnet, we were having an incredible data point resolution, number of data here. I'm not talking about resolution in the NMR spectrum. I'm talking about number of data points in our graph, and we, which is more reliable. And we basically demonstrated that this is the best way to really look into that. So we are flying here. So anyway, so our lessons learned from the because being 45 megahertz is, as we all know, permanent magnet, no need to fill cryogens, very small, easy to install, easy to use anywhere with installation, easy to maintain. And then the cons are, as explained before, low sensitivity, low resolution. That's a problem for complex system. The permanent magnet is in a fixed, at least my pico spin in particular, is in a fixed temperature at 42 degrees. So we have to measure at that temperature. So if our reaction is happening at a different temperature, there's a liability, there's a problem there. And in my case, I was limited to the number of nuclides, but now the Benchtop NMR has evolved at a much wider range. For the HTS 400 magnets, again, the benefits of no need of liquid cryogens. I don't need any high ceilings, extra space with the big liquid nitrogen and helium tanks. So that's why we put the instrument, the magnet in, and the whole thing in the chemistry lab, completely integrated. It's a smaller footprint than a standard cryogen magnet, a magnet system. Installation is relatively fast. And as a user, I shut down the instrument, I energize the magnet, it's very easy, and it's very mechanical. It's like the old cars with the carburetor, very mechanical. So you don't have to be an engineer to do those things. Because it's a high field and it's designed to use standard probes, so we can use variable temperature probes, we can use broadband probes, acquire any nuclide. So that's it's a great thing. The cons is you need to have a control on your power because power outage will get your magnetic field out. So then we have a UPS, or if you use generators, in our case, we have it connected to the UPS. We just still have some real estate need because you need to have the helium compressor, the power supply, and the chiller. So you need to have some space, right? It's very noisy. So I think I now talk louder, not because anything else, is because I am used to this noise on my head, you know. And well, in terms of this last point, is obviously in any NMR, when you use a big dynamic range with your solvents, and especially if they're protonated, you're going to have to use potentially suppression techniques, but that's not just specific to this one. So just briefly want to say thank you to many people that worked with me and participated, from Bruker, from HTS 110, and from Amgen, and special thank you to James with participating and working with him in the kinetics platform at Amgen. And I am done with this. So thank you very much. And if you have questions when the time comes, I'll be happy to answer. Thank you.
Thank you very much, Maria. That was a really interesting talk. Showed a lot about how, you know, NMR is really powerful for following reactions and understanding reaction mechanisms, and also for optimizing reactions. And your insights into comparing a benchtop system with a 400 megahertz HTS system are certainly interesting. And as you pointed out, some of the limitations that you encountered with the benchtop system have been developments in benchtop systems have overcome some of the limitations that you mentioned there. Just want to say we're going to move on to the next talk, but please feel free to ask questions via the chat window. I'll be fielding questions to the panelists once Travis and David have given their talks. But now I'd like to move on to Travis, and Travis is going to be talking about implementing benchtop in a manufacturing environment. So take it away, Travis.
Thanks for the introduction, Paul. Like I said, my name is Travis Gregar. I've been at 3M for a little over 20 years now. And I think if I'm not around to answer questions, I think Paul can also answer some of these questions because he and I spent quite a bit of time working on this project. This started about maybe 5 years ago as I was walking through downtown Atlanta with Tony down there, where we were talking some of the problems that he was encountering with a product that we make, that really the only way to determine if the material was good or bad was actually coat it on a web. And that really set things back in terms of generating a huge amount of waste. And so Tony wanted to buy a full-size NMR for one of our factories, and I was shocked and awed at the time, and I had to talk him back from the cliff because maintaining a high field instrument is a big deal, as already has been addressed by some of the speakers, namely in terms of cost, cryogens, and personnel. So what I was able to do is float the idea of using one of these low field instruments to see if it's even possible. All right, and so that's where we're going to begin. All right, so why are we doing this? We're trying to reduce the waste costs associated with this particular product. And what I knew at the time was there were only 3 components. And for proprietary purposes, we're just going to call them A and B plus a solvent. Now, Tony had tried previous attempts at this by doing some semi-quant intensity using IR, but the issue was the material would phase separate into rather large domains, so he could not get the ratios of these 2 components. And then he also tried XRF as well, but he was only able to quantify, I think it was component B rather well, whereas component A did not have enough heavy elements associated with it that could quantify. So what he set out to me is, can we actually calculate the ratio between A to B, because that ratio was critical to the ultimate performance of this thin coating in our products. If that ratio was off, then everything would start to stick together, resulting in requiring disposable of the web that we were coating. As a byproduct, or as a stretch goal, we were also trying to figure out, could we calculate percent solids? And this really turned into an issue because there was not really any NMR instruments in any of the 3M factories, and there was very much kind of a barrier. I think as many people has experienced, LC-GC is definitely a technique that is well represented in factories, along with XRF. But because we had the pull from an experienced analytical chemist that we had collaborated quite a bit, it was much easier to grease the wheels, as you might say, to at least investigate this as a possibility for implementation at the factory. So again, the goal was to measure percent solids, but we needed to determine if we could get, that peak selectivity. As long as the peak is isolated with minimal overlap, then everything should work very much like the previous talk on coffee demonstrated. So I'm not going to go through this very much. These benchtop NMRs are extremely rugged, and they're becoming much more affordable. one of the issues is that, we had to make this thing and this setup usable by, at-line employees who were not NMR spectroscopists, very likely not chemists, but someone who's a technician who knows how to push buttons and look for differences between things. So we had to make this as straightforward as possible. And as I had mentioned, NMR, even up to 5 years ago, is very much, in some respects, still a very much of a black box that there is some apprehension about, because it's very hard to know if the material, if the NMR is working. All right, and I'm going to talk about that a little bit more in a moment. I'm not going to verification and validation. How do we know the instrument's working, both on the hardware side and the software side? And this is going along with that black box side of things. And what is our requirements and specifications going to be? Because if we have a specific A to B ratio, what's the window of specifications that is going to be acceptable? So, we had to validate this with other analytical methods to make sure that things are working correctly. But ultimately, again, it really comes down to, are the peaks resolved at this time? So I want to start with right here. This is the proton NMR of our solution. You can see that I've got things labeled, components A and B in the upfield region, as well as our two solvent peaks. Early on, one thing that, growing up with 400 to 600 megahertz instruments, I never had to consider C13 satellites. So, I chuckle at it now, but, when your gap between your peak and your satellites become an issue, then overlap of those signals can actually become a concern. So in comparison, we've got our mixture or solution coded or at 500 megahertz here, where you can see that these peaks are well resolved. So looking forward, it looked at least promising. And then blowing it up a little bit more, you can see this upfield region where at 60 megahertz, there's a slight overlap in this region where we might be getting a little bit of overlap from one of the impurities that we're seeing here from the triplet that could be influencing the integration. And we'll talk about that in a few minutes as well. But overall, it seems like everything seems to be pointing in the right direction. So what we did is we made up a series of materials with different A to B ratios at both 500, and we measured them at 500 megahertz. And at the time, we were just borrowing a early instrument at 43 megahertz. And what we were able to show is that, we had extremely good linearity between, what was the target solutions as designed, as well as, are we getting the same answer between the high field and the low field instruments? So we qualified both the linearity, the specificity, as well as the selectivity for these two components in the material. Likewise, we also looked at, looking at percent solids. So in this case, we looked at it both at 500 and at this time 60 megahertz, where, we did get a reasonable linearity associated with both instruments at different percent solids. And so what we were ultimately able to do is move this forward and use this as a QC technique to monitor, the alpha to beta, the A to B ratio, and show where things fell out of line. Because again, prior to this, there was no quality control associated with these coding solutions that specified this ratio, and the only way to know is to run it, and if it worked, it worked. If it didn't, you threw everything away. So right around this time, we had a management change at the factory, and Tony worked in the analytical lab for well over 40 years, and Tony, I love Tony. He's a great guy. and he had a lot of influence, but times are changing. And so we had to start to consider what the instrument was, how the instrument was going to interact with good manufacturing, GMP, basically. This was a controlled environment, and we had dived into this project without taking that into consideration. So, we really were starting to be asked questions about the instrument itself, the software, and how are we going to integrate this instrument into a regulated environment. So, looking back at the instrument itself, and how can we make sure it's working, other than just the green light that says the instrument's on and that the instrument shimmed correctly. Do you have the correct signal to noise? Do you have the right line shape? Are the pulse widths changing, or is the pulse width uniformity changing over your spectral region? Likewise, at the time, the software was not CFR 21A compliant. And so that started to raise some concerns about data integrity. It was not protected. Likewise, any of the macros that I generated to collect the data were not secure, so they could be easily manipulated. And so part of that whole security, we really needed to take it to the next level. So this is where I learned all about GMP, coming from a non-GMP lab. And so, when it comes to the three first tests that we were looking at, we grabbed these tests from, looking back at some of the literature for NMR qualifications in a regulated environment. And, for the first three is pretty much what we already did. The specificity, the selectivity, the linearity. But then we need to start looking at more of the accuracy, repeatability, and the reproducibility of the measurements. All right. And so what we did is we basically just started making up solutions and figuring out, how is the instrument working? So as far as the accuracy, we made up some gravimetric samples, and we were able to show that, depending upon the ratios of the alpha to the A to B, as we started to get to lower and lower values, the NMR did not work, and so we were starting to get too high of a percent difference that we were comfortable with to show that the instrument was not working as designed. Likewise, the percent solids seemed to work fairly well. All right, so overall, percent solids and the A to B ratios were working as designed, and so this fulfilled our accuracy. However, when we started to look at the differences between the oven, which is the tried and true percent solids, and the calculation by NMR, nothing can really impact or improve upon the oven. Now, granted, the percent by NMR took, a minute to calculate, and the oven percent solids took, 20, 30 minutes. In the end, they were still okay using the oven as the ultimate percent solids measurement. And I think the differences that we're seeing between the oven and the NMR really came down to how much water was present in those coating solutions, which was not being accounted for by NMR in these solutions, and we just couldn't measure for that at the time using the benchtop. As far as repeatability, we were able to show exceptional repeatability in terms of the ratio as well as percent solids, and we were very, very happy with these samples. So this is where we took, I think it was the same sample 6 times and collected it, shimmed it, and repeated the whole process 6 times, and everything looked very, very good. In terms of reproducibility, we were able to show between 2 different locations, between our factory as well as our a lab here, that the reproducibility was very good and passed the expectations that we were set out to do. Lastly, we were looking at sample stability to make sure that nothing changed with the sample. So if the sample aged, we would not see anything changing. In this case, it clearly demonstrates that the sample was good. So this alleviated many of the concerns of the GMP folks in the factory. Next, we had to address GMP side of things on the instrument. Next, we had to address some of the side's concerns on the software side. And this is where I really worked with the folks with Magertech to try to implement some things that are a little bit more controlled and secure. And this is where we were able to start with their QNMR software. This is not necessarily QNMR per se, but this is the name of the software, where we were able to implement these buttons that helped to just simplify the whole process, where basically they prep the sample, they put in the sample, and then just press a button, where with that button, I'm able to automatically shim the sample, collect the data, process the data, integrate it, do some basic math, and spit out the answer automatically. All right, and that did alleviate a lot of the concerns of the GMP folks, and we were able to demonstrate through due diligence that this met the expectations for the factory. And so, like I said, instrument qualifications as well as software qualifications were addressed in the GMP system. And then step back here in terms of controlling access, we were able to lock it down as far as who had access to the software. So now we have control charts. We collect the data, we process it, phase it, all this, and we have control charts that's automatically dumped into a running CSV file, so we can maintain and be confident that our coding solution is what it's supposed to be, and we are much more confident that when we run it, we will have a good result. So to keep things moving forward, in conclusion, we were able to really demonstrate that this benchtop method was the best way for using benchtop NMR was the best way for controlling and making sure the quality of the coding solution was ideal. We were able to show that both on the instrument and software side, the necessary steps to qualify the instrument in a controlled manufacturing environment. Since then, we've also they've bought a second benchtop NMR at this facility, and I'm happy to say we've actually bought another one at a different facility that is being used now. So this system has been a real game changer for the way that NMR is being done right now at 3M, and we're always looking for new opportunities to implement NMR to simplify things. The biggest barrier that I've seen so far is helping folks at the factory really understand, what does the data mean, and then give them some confidence that when they're looking at the spectra themselves, that they are confident that in what the data is telling them. So I guess that, the only other thing I would add as far as, standard best practices for instrument qualification on the IQ, OQ side of things, whether it's an ASTM method or some industry standards that instrument vendors that they can use to make sure that these instruments are being used appropriately. And final, Tony was our analytical chemist who pulled us. Terry was the management. Chris and Alex were also help on this side at our factory. But really, it couldn't have been done without the pull, from Tony to say, we need this. This is what we need. This is how it's doing, and there's no other way to do it. And so, with the help of Terry, Chris, and Alex, we were able to do this and do it successfully. But and last but not least, I want to thank Paul. That was a lot of fun working with Paul at the time, learning the ins and outs of the hardware and the software. And lastly, certainly want to thank everyone who's online, and I plan on sticking around for questions. So thank you.
Thanks very much, Travis. That was a great talk. You covered a lot of ground there. You talked about a lot of the the issues around, or potential issues around, implementing a benchtop system in a manufacturing environment. You know, and you covered lots of things that hopefully we can touch on during the Q&A session. So I'm going to march forward and ask David to continue and round off today's presentations.
Thanks, Paul. So today I'm going to talk about, similar to what Maria spoke about earlier, is using Benchtop NMR for reaction monitoring in the pharmaceutical industry, and touch on like some of the applications I've been involved in the past and some of the opportunities as I see it that currently exist. So why is this important at all, right? And really, I took this from a paper about 10 years ago now, but I think it really captures the reason why we do this work. And to paraphrase, really, it's about, to really have a robust reaction process, you need to be able to understand it, okay? And, there are other PAT tools out there, right? IR, Raman, multiple other examples of process analytical technology that's been used to look at reaction processes. But why would we want to add NMR to the list? And really, for me, it's about chemical structure, right? I think for solution state, I think NMR is pretty much still unrivaled in terms of the information it can give you about chemical structure in solution. And it's complementary to the other tools that exist out there, right? So it's complementary to IR, it's complementary to online LC. And often it can act as a translational tool that links that structure and the kinetic trends to those that are obtained from other analytical techniques. I think we saw earlier from Maria, she was using NMR and calorimetry and showed really good data alignment between the two. And in itself, NMR can be used as a reaction monitoring tool. So that, I'll define that in a second, but it's really about, tracking species over time using NMR. So when we talk about online NMR, again, it's about moving reaction solutions from a vessel or wherever the reaction is happening to the NMR and back in a continuous flowing fashion. And the data then that we can acquire using the NMR can give us kinetic information, structural information, like I mentioned earlier, some of the mechanistic details about what's going on in the organic chemistry reaction. And overall, you get an increased understanding of your reaction. And that's getting back to the opening quote I had, where we're now beginning to really understand the reaction to the point where we can build a robust chemical process that can be scaled up to manufacturing scale. So I kind of put these things in two buckets. There's the reaction monitoring, right, which for me is tracking the species over time. That's where you're getting your kinetic profiles. And that's where we think about more traditional PAT, right, where we're getting those kinetic profiles of a process over time. And then there's the reaction characterization part. And that for me is the understanding the structural part of what's going on and also teasing out the mechanism of the reaction. So I think that Benchtop NMR falls more on the reaction monitoring side than the reaction characterization side, but that's not to say that there can't be benefits to both sides in using a Benchtop system. And combined, the two of these give you the process understanding. And we can monitor reactions in an NMR tube. We just put everything into the NMR tube, stick it in the magnet, record the data kinetic course over time. And then, as I mentioned earlier, the online NMR is where you're circulating something from the reaction vessel, which is being stirred, etc., to the NMR. I think most people in this audience will recognize the advantages that NMR brings, but it's truly quantitative, right? You don't need calibration curves, etc., in order to get quantitative data. The broad range of chemical shifts gives us access to many handles of tracking many of the components in the mixture. And it's really important is that the NMR is non-destructive, and when conducted in an online fashion is non-invasive either. So by using NMR to get your analysis, you're not changing the reaction in any way, and that can be very important. And that's something that is affected by other analytical tools such as LC. This slide just touches on some of the ways you can do these things. As I mentioned, NMR tube. When I started doing this work many years ago, we used this LC NMR flow probe, And then during my time at Pfizer, we worked with Bruker to develop this NMR flow tube. And I think that's been the way that a lot of folks have gone in more recent times, is using an NMR flow tube over a capillary type cell. So one of the things I got asked many years ago is, why don't you just put everything in an NMR tube, record the reaction, and get your data? And it's much cheaper. You don't need to worry about pumps, etc. And this was a set of experiments I did with my colleagues at Pfizer at the time, where we looked at what were the kinetics of this aldol condensation reaction when it was conducted in an NMR tube, when it was conducted online, which is the blue circles here. And then this intermediate red line was what we call periodic inversion, where we did the reaction in the NMR tube, took it out, agitated it by inverting, put it back into the NMR, re-recorded the data point, took it out again, and so on and so forth. So really what this shows you is that the way you set up your reaction and record the kinetics can actually influence the data that you get, right? Where the actual reaction conducted in tube isn't really representative of the exact kinetics that you observe when you have agitation, etc., in your reaction vessel. So the kinetics are dependent on the monitoring method. So moving on to talking about some of the benchtop NMR, and I'll show some examples of the work that I have done in the past in the next couple of slides. But this is some of the information I garnered from the various vendor websites that the information I could get access to. And you can see right now, Benchtop has moved on quite a bit from, I think Paul mentioned in 2010 was one of the first commercial systems, to the point where we have a range of magnetic field strengths. We now also have multi-nuclear capability, and I think that's really important too, especially for reaction monitoring. So adding things like phosphorus, having some broadband capabilities, and I think fluorine is very important too in the low fields, the benchtop low field NMR space. We're starting to see some temperature control come into some of these instruments, and that's really important when you're looking at reactions, to make sure the the temperature of the reaction is regulated and consistent throughout the sample loop. And many of them now have their own flow cell or flow tube accessory. Maria gave very nice examples of the use of her 400 megahertz high temperature superconducting magnet, and of course we have the traditional high field superconducting magnets that are being used also for reaction monitoring. So this was the magnet we used back when I was at Pfizer, and this was from about 2014. This was an Aspect AI 60 megahertz. It's not benchtop as we realize it now, but as you can see here, it was on wheels and could be wheeled quite close to the chemical fume hood. And the initial work we did with this was, we had been doing reaction monitoring at 400 megahertz for quite a number of years before that time. And so what we wanted to do was look at monitoring the reaction with both low field and high field at the same time. And this instrument really started to make the analysis mobile, right? So we could think about bringing this to a chemist's fume hood in different parts of the building, the potential for kilo lab and pilot plant, or manufacturing environments like we saw previously now became a possibility. So this is the data where we were monitoring the same reaction, flowing in two directions. So we had one going to the 400 megahertz, one going to the 60 megahertz. And we conducted 3 different reactions here. The circles are the 60 megahertz data, and the straight lines are the data from 400 megahertz. And you can see that for each of these reactions, we have very good agreement between the data that's being that we're getting here. So really this is showing the power that the benchtop can provide, given all the other advantages that it has in terms of cost, etc., over the high field instruments. This is a second example where I worked with my colleagues in medicinal chemistry, and we were looking at a flow chemistry process. So this was a kinetic, enzymatic kinetic resolution experiment. And in this case, we had our vessel here and flowing some of these starting materials through this packed bed of enzyme, and then monitoring the output of that process over time. You can see here we were doing multiple types of analytical data here. So we had online IR, we had online NMR, we did some offline NMR analysis at higher fields, and also GC analysis, because obviously, typically NMR isn't going to give you that differentiation between enantiomers. And really what we're able to show here is that we were able to use the Benchtop system, which at that point we used a Magritech 65 megahertz system. And we could look at how the effect of the flow rate would affect the conversion. And you can see here, so this is the initial startup of the reaction. We've got to a steady state where the reaction was just going. And now we could look at the effect of the flow rate. How would the flow rate affect the conversion? And you can see here, I think in this region here, we were at 0.5 mils per minute. And clearly you can see once we up the flow rate to 0.75 mils per minute, which is in this region here, we got a drop in conversion, right? So we could use the NMR to help us optimize the flow rate for this conversion here. I took this data from a paper in 2021, and this is just kind of shows like the increase in the amount of publications that involve Benchtop NMR for process monitoring. And you can see the general trend over the last 10, 11 years has been definitely an upward trajectory. So there's definitely a lot of progress going on in the area of reaction monitoring using Benchtop instruments. I think some of this has been touched on already, so I won't go in detail, and maybe this can be part of our discussion, but there are some challenges, right? So resolution sensitivity can be issues depending on the reaction that you're trying to monitor. And as I mentioned earlier, the temperature range that can be achieved using some of these Benchtops systems is limited. So for me, some of the opportunities I see for Benchtop NMR in the pharmaceutical industry and for chemical process monitoring, an opportunity is around the temperature control, right? I think that's a key component to having broad adoption of these instruments for process monitoring. I think an integrated system, I think we're starting to see some of that. So, but what I mean by integrated system is where you have something you can buy off the shelf, right? That has a flow cell, has the hardware, the software, kind of an end-to-end solution. One area that I think, this is probably a broadly NMR audience, but I think these instruments are really beneficial for engineers and chemists, right, as the primary users, and us as NMR spectroscopists being facilitators to those people in their use, because they're the ones who are really going to get the greatest benefit out of these instruments. Fluorine is a huge opportunity. About 25% of active pharmaceutical ingredients contain fluorine. And then chemometric analysis. I think we've seen examples of where the spectral dispersion and overlap can be an issue at lower fields, and that's where chemometric tools and ways of analyzing the data could be very powerful. So I think with that, I will hand back to Paul, and just to say that from my experience, I feel that Benchtop NMR resides more towards the monitoring side than the characterization side, but that's a constantly changing situation. So hand back to you, Paul. Thank you.
Thanks very much indeed, David. That was very interesting, and I think the end of your talk as well, where you're talking about opportunities and challenges, was where I was my sort of setting the scene talk was going, in terms of I was getting to the point where I was talking about all these good things, and then you've touched on very nicely the kind of challenges that I wanted to bring up, and I was hoping would be something that we could continue as a discussion. So I would could you stop sharing, actually, David?
Yeah, sure.
Thank you. Okay, great. So yeah, we've had 4 excellent presentations today, diverse presentations that have talked about, I think ably demonstrated how useful Benchtop NMR can be, and what the, not just potential, but the current application of Benchtop, but also point to the potential of Benchtop in the future. But I think another side of that as well is, what challenges there are. Now, we are short of time, so I'm actually seeing, I'm very pleased to say, some questions coming in on the chat. So I'm going to field some of those questions first of all. So please, folks, if you've got questions, please feel free to enter them in the chat window. Also, you can use your mouth as well, and you can unmute and talk and direct the questions to the panel as well. So here's a question from Hector, and this is Hector Robert, and he said, this is a question for you, David. He says, what is his assessment of the future of low field benchtop for reaction monitoring in pharma?
So I think the potential, I think we're getting to a point where there is going to be broader adoption of these benchtop systems in pharma. I think a lot has changed in the last 10 years, and I think we're with a few adjustments and tweaks, etc. I think we're close, right? And so I guess in a nutshell, my answer is, I think the future is bright. We just need to get over a few more obstacles.
Sure. And those are the kinds of obstacles that you mentioned, just summing up at the end, really. Yeah. And I guess things like method validation and all of that side of things, and also things like GMP that Travis touched on as well.
Yeah, for sure. And I think it depends what your application is going to be. I've typically worked in the development space, right? So there we don't necessarily worry that much about GMP. But obviously, when you think about like the type of work that Travis has done, and you move to the manufacturing environment, obviously that's a big concern. Yeah,
definitely. Thank you for that. So Tim has asked, he said, some very nice examples given here. Has anybody explored the use of 2D experiments on Benchtop and found any uses and applications? I'm sure that there's probably some people in the audience who could answer that better than I have, but certainly, like I was saying, and I don't know if I got cut off at this point, my internet decided to throw a spanner in the works at that point, but certainly 2D is standard, is, now, just commonplace, if not standard on benchtop instruments. So obviously, when you work at lower field strengths, you have some potential issues with dispersion. 2D helps to overcome, by spreading your signals out in an extra frequency dimension, you're overcoming some of that overlap or that lack of dispersion. So as a tool for getting structural information, 2D is already being used. But if you're but I know that other, 2D has been explored in the context of things like reaction monitoring as well. So I've seen some examples of 2D being used for reaction monitoring. I know Patrick Girardot's group has also done some things like ultra-fast 2D for rapid reaction monitoring using, as I say, using ultra-fast 2D methods like the kind of EPI type methods. So there's definitely potential for 2D to be utilized for things like reaction monitoring as well. And I think there's a lot out there. There's more stuff out in the literature there. So yeah, any more questions from folks?
This is Krish.
Hi, Chris.
I want to talk about a little bit on some questions related to the reaction monitoring that you guys were talking, David particularly was mentioning. How do you deal with the there is an intrinsic sensitivity issue, right? So your reaction monitoring is constrained by being able to monitor in a higher concentration, if you may, higher than what you can probably live with in a high field. So that adds a constraint to the kind of reactions that you could potentially follow. So, so to the bigger audience, are there better approaches to deal with post-acquisition deal with your sensitivity issue? Are there software tools that people are using to deal with your raw signal to noise issues post acquisition? So you could now tie that disadvantage of lower signal to noise, because even if you have a signal to noise of 10:1, there is an uncertainty that leads to uncertainty. And recently, Gennady from Genentech published a very interesting paper in analytical chemistry, where noise is an issue in quantifying a signal. And how do we deal with this in a bigger picture?
That's a great question, Krish. I don't know if there's anybody in the audience who can kind of address that question. Somebody who's been involved with data analysis, data processing, but it is, it's like a really obvious question. We talk about dispersion limitations and challenges with overlap, and I Krish, you obviously been very active in working in the area of things like craft. What about the whole business of sensitivity? So if somebody's got some insights into that, would be great. Anybody?
Sounds like an opportunity.
Okay.
If I go ahead, somebody has an answer. No,
I don't think
so. Okay, so because something light up on my screen. So no, the reason I am trying to bring this up is some of you probably heard me in several other meetings as well. Signal to noise definition is where in FID, the signals on the front end of the FID have large signal to noise. Later part of the FID have a poor signal to noise. So whereas in the after Fourier transform, the noise is across the entire frequency domain, RMS. So I was just bringing it up to, we have been working on that area of how to exploit this different higher sensitivity on the front end. And it's not anything new. There had been other approaches in 2D, for example, many years ago, sampling more, for example, heavily sampling at the higher end, front end of the interferogram, and less sampling. Now, when I say sampling, even the number of scans can be different and scaled up later. Non-uniform sampling is another one in the 2D. So there are value to exploiting the higher signal to noise on in FID on the front end, and then the later part of the FID. So
yeah, I think Krish, was it in the last Ivan session or one of the recent ones where you had a very nice slide that demonstrated, using the early part and neglecting the later part and the impact on signal to noise to follow.
Right.
It was quite convincing. Obviously, the other thing related to sensitivity is the use of hyperpolarization as well, which is something that has been done to enhance sensitivity in conjunction with the use of benchtop systems.
The thing which I find it interesting is invariably we do, there were some examples of from in this talk. Kate showed an example where that peak was, there was a peak that she was, I forget the name of that compound.
It's that 16 OMC.
Right, exactly, yeah. So invariably we are looking for a higher window of opportunity around the peak of interest than the peak sharpness itself, right? If it's a 1 hertz peak aligned with peak, we tend to look for a peak that is plus minus 5 hertz, empty on either side type of thing. Good old QNMR, or we go into deconvolution methods and things like that. And that very fact it means to me is we are already focusing on wider frequency resolution. If I may be using words that are phrases that can be confusing, but we are okay with poorer frequency resolution when we are focusing on amplitude or integral of a peak. In other words, when we integrate 10 hertz. That means we are okay with 10 hertz of frequency resolution. So how can we exploit that? If we're willing to accept that, I mean, that's not accept, it's a conventional wisdom. How do we exploit that conventional wisdom to not worry about trying to collect 1 second of data? What do we collect 1 second of data if you are looking for a 10 hertz window as for quantification? So I'm just throwing this out as a discussion points rather than preaching.
Is what you're saying, Krish, that it is changing the nature of what you collect to focus on the thing that you're looking for? So instead of, I mean, that's exactly what we've done. We've ditched some of the sort of conventional things like looking at what the right RD should be, and gone by what works in practice in order to try and minimize the length of time we have to collect overall. So for instance, in the coffee work, we do need to collect a lot of co-added scans, so that takes about half an hour to collect those spectra, because the component we're looking for is present in such tiny quantities. We're really pushing, I mean, that 16 ohm C is sort of mgs per kilo in terms of what its present is in Arabica. It's sort of about 10 milligrams per kilogram of coffee beans, so it's a tiny component. So we have to do everything we can to amplify the signal to noise, so collecting a lot of coded scans. And obviously we don't want a massive RD so that the whole thing takes hours, but we didn't find it had any negative effect. We're only focusing on that tiny region. We don't care really what the quality of spectrum looks like elsewhere, and we can check for linearity that we're not, you know, saturating and just like upsetting things. We're just focusing on that one thing. And so, for instance, the use of that north filter as well, the matched filter, that's an old signal processing trick, but it's exactly what we want, because we just want to know about that one region. So we look for the shape that we're expecting and scan across that one region to find, you know, a cross correlation optimum. So I agree with you. I think a kind of paradigm shift is the right way to go for Benchtop, because we don't have to be constrained by what people have done for the last 20, 30 years. We can think about this in terms of the quality of the data and what statistical or chemometric techniques you might want to do to get the best out of it. And that would be my view. I mean, I suppose that's kind of where my background is, so I come from it from a data scientist point of view. But things like stability and reproducibility and yeah, definitely non-subjectivity. So for instance, another thing that I like to do is not use phase corrected data at all, and to do pattern recognition using magnitude spectra, because then you ditch the whole subjectivity of somebody doing phase correction. So I think there are lots of things that having a new approach, having a new eye that Benchtop spectroscopy is, can it's a chance to do things in a different way and to get the best out of what you're trying to achieve.
Yeah, I think Krish has very strong opinions about about phase correction and all of that. Yeah, I totally agree with you, Kate. It's you know, it's about as you say, not just doing things the way that they've always been done, because that's how people think about these things, and actually focusing precisely on the problem at hand and using the right approach. But I mean, one of the things that we haven't touched on today is just, and I know this is going to come next month, so it actually don't feel so bad, or the next Ivan session, because I don't feel so bad that I didn't spend much time talking about it or mentioning it when I got cut off, is the whole role of advanced data processing to overcome problems like signal overlap. And I think that's really where that's going to play a very important role in the Benchtop NMR kind of fulfilling its potential and becoming more usable in a wider range of environments. So, you know, and I know there are folks here who have been on the meeting today who are very active in doing that kind of work. Chris being one, Matthias Niemitz and his work with quantum mechanical modeling, for example, and the same with Daniel Holland, who is going to be on the next Ivan session. So I think there's a lot of, you know, you've got to overcome some of these limitations, and there's only so much you can do with the kind of time-honored approaches to analyzing an NMR spectrum, and these methods are going to be really important in the future. For certainly as you automate, and you know, the whole thing with Benchtop NMR is about is turning it into something that solves a problem rather than think of it as an NMR spectrometer. As Travis was talking about, you know, and you've been talking about deploying it in somewhere where you haven't got specialists and who are going to manually process data and all of that. You want it to be able to just be a black box and just pull out the quantitative information from the spectrum in, you know, without anybody having to intervene. And these advanced data processing methods are going to be a really important part of that whole development. But we'll hear more about that next Ivan session, I'm sure. So do we have any more questions at all? Because I know we're now.
And I just want to say, unfortunately, Chris, I don't have an answer for you, but this is an interesting problem because even in the high field, let's say we have a reaction when we have a catalyst with phosphorus. Even though phosphorus is 100% abundance, but the sensitivity and other things are not good. Normally, the catalyst is in a small quantity compared with what the reaction or reagents are. So we would like many times to understand what happened to the catalyst. And even in the high field, where you have more sensitivity, we cannot see it. If there is a way we could figure it out, how to see also signals from the catalyst, that would be tremendously helpful for our understanding the mechanism of the reaction and how the catalysts act in these intermediates, whatever. But yeah, I wish I have an answer. I do not, but thank you.
Thank you, Maria.
Okay, any more questions? Anybody?
So I'll break in here. So if there are no more questions, maybe this is the time for us to adjourn. Okay, so before we go, let me hand things back to John.
Well, all I can say is absolutely fantastic. Paul, David, Kate, Travis, and Maria, over the top, as they say. Here's the problem, though. You guys keep raising the bar for us. Well, I say that tongue in cheek. Obviously a good problem. Well, not a problem at all, but absolutely fantastic job with this. Very broad reaching topic, clearly very broad interest. And well, last but not least, very clearly that Benchtop Fourier transform NMR has, well, it's come of age, hasn't it? And this has been certainly very enlightening. Today, we thank you, our panel. We certainly thank all of the participants and audience members for joining us today. Don't forget, toward the end of April, April 23rd, I think is the date. Hopefully we'll be live and in person day before ENC. Don't forget the Ivan Founders Award nominations. We certainly need your valuable input on that topic. And certainly a number of other meetings, regularly scheduled meetings coming down the pike. Dave, that's all I've got to say. And if you're ready to gavel us out.
Okay, thank you. For those who haven't seen it before, I have my nifty Ivan gavel, and so I'll adjourn the meeting.
Thanks, everyone.
Bye-bye, folks.
Thank you.
Thanks, everybody. Thank you.
Thanks.
Bye.
Bye.
Cheers.
Thank you.
Bye.
Bye.
Bye-bye.
Thank you.